is it visible to everybody?
Yes. Yeah.
Okay. So I'm just going to talk about, so Aranya Innovations and Research is actually set up like a non-profit, and the idea of this organization is to take forward sustainability innovations that are actually in the academic space or being promoted by small time or people who have not yet scaled out, and then take it in a way that we can incorporate it in public projects within tenders and so on. So you might be knowing about Samagra. They do a lot of good work in the area of public infrastructure. So we are trying to do that, but for more specifically for sustainability projects. So today I'm going to be focusing on a technology that we promote for wastewater treatment. It's called the CAMUS process. Essentially, it integrates soil ecology for wastewater treatment, and like any of our high-tech cell phones and things like that, the process actually is an amalgamation or an integration of nature-based solutions that have been developed at different academic institutions. I'll talk about it a little bit more. Some of it was developed in collaboration with Professor H.S. Shankar of IIT Bombay and Vision Earthcare, which is a nature-based technology provider at IIT Bombay. I have an association with them also. I head the research at that location. So yes, so what does Aranya do? We are actually looking at design innovation interventions for public projects. So incorporate novel concepts via CSR. The idea is to design parks, recreation facilities, outdoor facilities. So we have done things like in a small scale, things like designing, public rock climbing walls in Navi Mumbai. Things like there's like public parks are not very well designed in Mumbai. So giving designs for things like basketball courts, and of course this is not sustainability, but really improves the quality of living. And my own, when I came back from the US to India, I felt that there's so little to do outside. You don't have any facilities, or if the facilities are created, they are not maintained properly, security is not proper, and so on. And that's something which I feel should change, and Aranya is trying to do that. Sustainability projects, I'll give a list a little bit later. And the most important part, what really happens is that in the government sector, assets are created, but assets are never managed or maintained so that people can actually enjoy them. And that's something that we are very keen on doing. So we are also technology providers for nature-based technologies. So the CAMUS process is an integration of the SBT patent of IIT Bombay, the Metrol patent of Professor H.S. Shankar, IIT Bombay, and the ABGS patent, which has been developed at the College of Engineering, Pune. Then we have solutions for lake and nala treatment, which is Aranya Dwip, which is actually a purifying island. I'll explain a few pictures of it in the future. And then the Chefrol process, which actually uses floating aquatic plants. This is something that we are now integrating into our mainstream wastewater treatment plants as a replacement for conventional settling systems, which I'll explain in some time. And we have concepts of sustainable urban planning called Peacock EcoCity, things like sewage irrigated forests. So basically agroforestry. Can you actually see, most people think of wastewater as a liability. It's things that pollute our lakes and rivers and so on. But really speaking, this can be integrated to create green spaces without creating nuisance. I mean, and you can actually generate value out of it. An initial project has been pitched to our, as Ganesh might have explained, we are a consortium of companies that work under the LEAP umbrella, headed by Manas Rath, also in Mumbai. So we are now pitching a concept of trying to create this treated water agroforestry using bamboo and other agroforestry products. So hopefully that tender will come out shortly. So what is a sewage irrigated forest? Everybody knows, you can actually grow teak, lumber, bamboo and things like that using water. It requires water, and wastewater is available in plenty in India. If you can integrate this, integrate sewage irrigated forests with this wastewater, Of course, you have to take care to make sure that there is no mosquito menace and other things like that, or you do not grow too many food items, because food, of course, with wastewater, we don't know whether it is safe enough. I am happily eating sewage irrigated, spinach and other things which is available in Mumbai. So no complaints there, but maybe other nations may not accept such practices. But in any case, the waste in the sewage is actually a resource. It's a natural fertilizer to trees and plants and other things like that. As long as you're able to load it in the prescribed amount or the prescribed kiloliters per acre, then you should be able to get very good results and get good solutions. So the second technology that we promote is this Nala rejuvenative technology. Now, this is something that we have licensed from Pondicherry University, and it actually uses floating aquatic plants to treat wastewater. So what you're really seeing is it's called the sheet flow root level system, where the wastewater actually goes crossways across the root zone of these aquatic plants, and the aquatic plants actually pick up the suspended solids, and the microbial action takes place at the interface of the water, the root zone, which is also exuding biocoagulants and flocculants, and therefore doing the treatment. So of course the treatment doesn't happen to the full extent, but this is a cheap way of removing about 60 to 70% of the waste load of a nala that goes into a main river. So we have already done I think a 2 MLT pilot at Mandideep in Madhya Pradesh. So that's something that we are going to scale out in a larger way. So idea here is that yes, the NGT norms say that you have to get to very high treated water quality, but really what happens is that most municipal authorities do not have the funds to either build it or maintain it. So in the interim, while they are developing these projects, the Chevron process actually reduces or partly ameliorates the load on your lakes and rivers using an engineered ecology. Okay, so this is how it works. You have like a silt trap that traps all the silt from the nala. So you can remove that once in a while. You have a floating trash barrier that picks up all the plastics and things like that. This is something that this is a company out of I want to say Bangalore, and they provide these floating trash barriers. And post that, they have actually done many interventions. This is meant for deep flows, but most of the nalas are actually quite shallow. You would see that the water in those nalas is never more than 5 to 10 centimeters deep. So in those locations, we have to put in a bar screen and so on. But for much larger nalas, you can do this. After the silt trap, you have like a weir. The weir actually then flows into this floating aquatic plants, which then remove the TSS and so on. So depending upon the flow in the nala, we choose the length and the width of this system. There is also an online monitoring system that I can talk about later. It's a floating online monitoring system, and it has been installed in multiple locations. So if you want to maintain, if you want to assess the quality of your public lakes and rivers and water bodies, we have solutions that you can actually push into your lakes and rivers that will give you like a real-time update of what the water quality is. It's a solar-powered, GPS-locked system that allows you to see what happens, and you can actually use it to see if an intervention that has been provided actually gives you treatment or not, and how it changes. You can also easily understand whether like there's a peak pollution event, like a flash pollution event, maybe an industry discharging a large amount of wastewater into a nala or a river or a pond, that can be easily assessed by having such systems. So this is the second technology, and this is another technology which is for lake remediation. So this is not for a nala. So you might see that you might have in Bangalore and other parts of India, you will have all these lakes that have been infested with floating vegetation that have been because of the influx of wastewater and so on. So what we have really done is that our understanding of soil systems has allowed us to come up with this design. So basically, we create these small soil volcanoes, you might want to call it that, but essentially it is these it's these islands that are populated with these trees. And what we do is that we load the center of this island with your wastewater, and that wastewater then percolates through this island and then reaches the water body. In the process of percolating through this island, which we call as the Aranya Dwip, which is the Aranya, the word actually is forest in Sanskrit. So forest island is a purifying forest island, which then picks up all the waste nutrients from this wastewater that we have loaded and converts it into pure water. And not only do we do this, we also, in the process of creating these purifying islands, we are also desilting the lake. We are creating green spaces that are habitats for birds and other small animals, and that actually creates, from a destroyed, polluted water body, you're going to get like this tourist space. The pictures that you're seeing here is actually implementation in Salem. There's a pond there, which is now converted into this famous location. And that is being done by Salem Citizen Forum by Piyush Manush, actually. So you might be knowing about such CSR initiatives already, but the idea is that to take this from like a small implementation to larger implementations across India and perhaps across the globe, that's the idea with which we are moving forward. And then we have this Peacock EcoCity urban design. So essentially we all know that urban spaces are drivers of innovation. And the idea is that once we convert this into concrete jungles, you are going to have massive sustainability and ecological problems. It's going to be unlivable. I can see that, I live in Bombay, and all of you know that there are two parts of Bombay, maybe. One part is the old Bombay, which is the island part of it. People maybe want to compare it with Manhattan, but of course it's nowhere near Manhattan standards in terms of infrastructure. But on the other side, you have Navi Mumbai, which is a planned city, and they have done a fantastic job of urban planning. There are parks, there are lakes, there are sustainability. For whatever reason, I don't know if they actually had a plan like this, but the development of green spaces in terms of having all these other ecological facilities has been put in place. So inspired by all these ideas, and also inspired by the time I spent at IIT Bombay, which is actually a verdant forest, and then you have all these small buildings in the middle. But what I really loved about these green campuses is the fact that the forestry within these campuses actually can be integrated as a recycling forest. So that recycles your solid waste, that recycles your liquid waste, and also provides the air purification and heat management by the evapotranspiration that is engineered into it. So these are some concepts that need to be implemented. So we are working with city master planning authorities to essentially tell them that please do not give builders like small plots. Let them actually build into a 3-hectare plot where they have not only do they have to provide the living space, which here you can see is this connected building, but also the central recreation space and also the recreation facilities without impinging on nature. So in this concept, I'm not going to spend too much. Ganesh or Sharmila, can I know how much time I have? I've already done 17 minutes.
Yes, the talk ideally goes on until 11:30.
Oh, okay. Sorry, I have to speed up then. Okay. All right. So these are some videos that I'm going to show, but anybody can, people can come and talk to me or send me a message later. I'll be happy to share. Okay. Right. So I'm coming to the main course, which is the CAMUS wastewater recycling process. What you're seeing is a collage of projects that have been done across India, and I'm going to explain this in some detail now. So what you're really seeing is the top of a 3 to 3.5 meter soil-like media. So when I say soil-like media, it is it's not actually soil. So the technology was initially, when the initial research in this technology started in 1990s by Professor Shankar, where they actually used red soil to do treatment of wastewater. So at that point, the technology that was developed was called constructed soil filters. And many demonstration plants were created by using this technology. The first one being in Indira Gandhi Center in Borivali in 1993, I believe. That's what I was told. And then in 2001, again in I think Kanjur Mart, they did something. And these were the first pilot demonstrations. In 2005, this project was implemented in BMC, which is Bombay Municipal Corporation, now called MCGM. And this is a 3MLD project. And you can see this lake here. That actually is the lake of treated water, which is then, the treated water lake is then used as the source for irrigation in the Mahalakshmi race course and the Willingdon golf course in the Worli region. I think it's about 1.5 kilometers away. So this was a 2005 implementation. And at this point, we had moved from the soil-like media that we were using, which is taking a lot more space, to this granular porous media, which became the, it's sort of like the seed for the new CAMUS technology. Okay, so when we started going to market with this technology, the first challenge, and we obviously being in a metro city, we went and talked to a few developers and others, and they basically said that at that point the technology was using like 2 square meters per KLD. So they said that kind of space we don't have, and first of all, I mean, we are paying our taxes, so we are just going to put it into the BMC underground drainage system. So we are not really interested. So of course, so we started working with the government to try and solve their wastewater problems. But obviously in metro city, space has always been a constraint. And with this amount of area that was required by the old constructed soil filter technology, very quickly we realized that that is not going to be an acceptable solution in the coming years. So a huge amount of research started to reduce the space required. And I'm happy to say that the CAMUS process today uses only about 0.6 square meters per KLD. So almost a 3-fold reduction in the space requirement has taken place. And that is what has allowed us to become one of the largest. In fact, I've been tracking this nature-based technology space for quite a while. There are lots of very interesting players from Israel and many other places, and even from India. There are lots of people promoting nature-based technologies, and I'm 100% confident that these nature-based technologies actually give a better solution than the conventional irritate technologies that are being implemented. The big advantage that we have seen in the last many years is because we use about half the space and we do not need activated carbon or a sand filter at the end of our process, we are getting very high treated water quality. So this is the 3 bottles I'm showing at the bottom is the wastewater that comes in. This is the treated water, and this is drinking water for comparison. So essentially, when you take treated water from our process, it actually looks very similar to drinking water that comes from your tap. And therefore, the acceptability and the usability is much superior. So this project, for example, is a project that is less than 10 meters away from the living spaces. And the water from this complex is treated and used for flushing, of course, then lobby washing, car washing, all the irrigation facilities. And the excess water, of course, if you want, you can use it for construction. At the time when we started this project, this treated water from this section was used in the construction on phase 2. So the builder saved a huge amount of money there. This is Devprayag, which is the confluence of Bhagirathi, Alaknanda. You would know that's where the river Ganga actually starts. And this is the 1.4 MLD plant that's in that region. So we have multiple places. I'm not going to show you this for lack of time. I have 7 minutes. Right. So I am going to come to what really a typical municipal project is. So of course, I'm talking about a municipal project because the design of a municipal project is different from the design of a private sector project. I will show you both, but this is something which would be instructive. So what you're seeing here,
we find the wet well of the Punderford 2.5 MLD CAMUS SBT type.
So this is the wet well. So if you know anything about sewerage, so I'm just going to
screen where plastics and other.
I'm going to turn off the this thing. So this is the wet well. This is the core screen. So you have this underground. You can see the wastewater coming into your into the wet well that goes through a core screen. This is about 10 mm screen width. And from there, it is pumped from this location. So obviously, most of the time you will not find the wet well may be in one location and the space allocated for the STP is in some other location. So here actually it pumps from here to the STP is about 500 meters away. And these are just pumps. So this is the wastewater entering the first stage of our plant. So the first stage in any STP technology, of course, is a preliminary screening where we are taking care of finer particles like this gutka, chilkas, and thread and hair and other things like that. So here the 5 mm screen actually filters out all this suspended solids and then transfers it into the first settling basin. Okay, so this settling basin that you're seeing on the right side, currently we are also implementing what is called as the floating aquatic plants for suspended solids removal. So those plants will come. This is a plant that was commissioned in 2017, and this location actually is being provided because as the norms increase, they may ask for biological phosphate removal and things like that. So here is a place where you can dose with iron to remove phosphates and things like that. So here what happens is that the suspended solids, sewage solids, which is fecally rich sewage solids, will be there. So separate out the organic and the grit part of this of the sewage here, and clear water goes into the next stage, which is what we call as an equalization tank. So you will be interested. Obviously, we all know that most of our bathing activities or water use activities in our houses happens in the morning. So we need a tank. So obviously, most of the water comes from between 6 o'clock in the morning to about 11 o'clock in the morning. So that peak has to be handled, and we usually do that with an equalization tank. So this equalization tank collects the clear water from the clarification step, and the clear water is then sprinkled into two bioreactors. You're seeing the first one here. What you're seeing, these white posts are actually a distributor network that distribute the water across this this area. And of course, at that point, the plantation that we had done on the bioreactor was small. So the first stage, the treated water is collected in this treated water tank called collection tank 1. Here we mix a residual amount of water from the equalization tank. So the mixture of nitrated water that comes out of BM1, as we call it, the first stage, and the ammoniacal water that is coming directly from the equalization tank is mixed here and then dosed at a higher hydraulic loading rate into the second reactor. So basically then this second reactor acts as the denitrifying step. So in this stage, we are removing the ammonia and nitrate mixture out as N2 and H2O and oxygen. The oxygen is used for final treatment of the COD, which is present in the equalization tank water. Now you will be asking what is happening to the sludge. The sludge from the bottom of the settling basin is vermicomposted. So this is using the SBT patent. So of course here we are seeing all of it open, but the way to load it is you load one cell per day until it is full, and then you leave it for dewatering, drying, and vermicomposting. This is using the Ferratima elongata white worm, which is present in the soil right below this. So that's the basic process. So I'm now left with 3 minutes. I'm going to go ahead and talk a little bit about what is really happening is that the media, the wastewater comes in contact with this porous granular media. The organics are weakly adsorbed on the media internal and external surfaces. And the media is chosen in such a way that it becomes the home for these soil mites. So people, very few people know about, everybody probably knows about earthworms, but as our research actually showed, in many of these hard porous soils, it is these soil mites that are the top predators of this ecosystem. So the top predators then harvest or cull the bacterial films or the fungal films that are growing. So one of the other parts of the innovation that we have realized is that in most other treatment processes, we are using predominantly a bacterial culture, but the CAMUS process actually uses a significant amount of fungal cultures. So what happens with fungal cultures is that they are far more efficient enzymes produced by fungal cultures for breakdown of complex molecules, and therefore the efficiency is actually increased quite a bit. So the earthworms in the arbuated colonies inside, they feed on these films of fungal and bacterial films that are growing and then regenerate the surface, and the surface is then available for the next cycle. So this cycle continues, and I'm left with 1 minute. And I wanted to talk about, well, can I go a little bit further? I mean, I might take a couple of minutes more. Is that okay?
Yes,
Hello.
yes, like another.
Sharmila?
Sure, Karthik. Yeah, please.
Yeah, of course.
Very interesting.
Hello. Can you hear me?
Yeah, yeah.
Yes,
yeah.
yes. Please go ahead. Please go ahead. Take a few more minutes. Not a problem.
Can you guys hear me?
Yes, we can hear you.
Hello.
Hello.
Hello. We can hear you, Karthik. Please go ahead. Please.
Let's see if we can do this again. All right. So now I wanted to spend some time in explaining why soil is critical for the treatment of wastewater, and this actually comes from the design of nature itself. Now, if you look at carbon in our on Earth, okay, it actually transfers between the hydrosphere, the atmosphere, the lithosphere, and of course there are fossil reserves below our in the lithosphere. So if you look at the atmosphere, you have about 750 billion tons of carbon in the atmosphere, and we all know it is actually increasing now because the fossil extraction is taking place in a big way. And if you look at land, there is about 500 billion tons as living carbon. So when I say 500 billion tons, just you and I, if you are 70 kilos of say weight, then our total living carbon that we will have is about 5 to 7 kilos of living carbon. Okay, so if you measure all life on Earth as living carbon, land-based plants are about 500 billion tons, and land-based animals. So of course, remember this, almost 99% of all life on Earth actually resides in the thin shell about 2 meters below our feet to about 2 meters above the ground. Okay, so that's essentially where 99% of most life on Earth resides. So when I say 2 meters, of course, big forests and all that are of course much taller, and you might have up to about 30-40 meters of tree cover. But if you look at the Earth as a whole, rainforests are a very small fraction of the green cover that we have. So that's about 100 to 150 billion tons of live carbon. If you look at water, water contains a huge amount of carbon dioxide dissolved as inorganic carbon dioxide. So what we know as carbonic acid or whatever it is, HCO3. So this is not living carbon. If you look at living carbon in water, it's only 1 to 5 billion tons. Now, if you look at the biological amount of carbon transferred from water to air, biology actually respires 60 billion tons per year into the atmosphere. Whereas the land-based animals and plants, that's 650 billion tons, respire only 30 and 12 respectively. So that's about 42. So look at this number here. So let us say about 3 billion tons of life on water is respiring 60 billion tons of carbon into the atmosphere. Whereas to sustain 650 billion tons, you only need 42. And also remember this, that land is only 1/3 of the Earth's surface and water is 2/3. So essentially speaking, the productivity of land in terms of sustaining life is much, much more. The reason for this, and if you do the basic calculation, you will see that land you need only 3 kilojoules per gram of live carbon per year to live. Inside water, it is 500 kilojoules per gram live carbon. So really speaking, if you want to be more sustainable, remember that it takes a lot more energy to produce aquatic life than produce life on land. It's one of the reasons why life, even though it began in water, it very quickly moved to land because the availability of oxygen was much better. Soils have higher diffusivity of oxygen, and the diffusivity is much, much better too. Whereas if you look at water, the maximum oxygen that you can transfer is about 6 ppm, and 6 to 8 ppm, but the diffusivity is about 10,000 times lower than in air. So obviously, marine life has to spend a huge amount of energy searching for and extracting this oxygen from water, and that's the reason why you should never do waste. You should first of all never put waste into water, but if you have done it, then try to bring it back to soil, and that's what the CAMUS process does. I have extended by about 4 minutes.